So now that we've actually talked about what a vector is and what a scalar is, how about we start actually doing some math with these concepts. So to begin, we're going to start with a very, very basic concept, adding two vectors together. So for these explanations, I'm going to have two main vectors. For now, I'm going to add a third later on. This is going to be the a hat vector, and in purple is going to be the b hat vector. These should be very similar to the ones that you can find in your book in section 1.2. And for our first task, what we want to do is we want to see what happens when we try to add these two vectors together. And hopefully you remember from like a mechanics course or a statics course that one of the simplest ways to actually perform vector addition is to do it graphically. And to be able to do it graphically, use the head to tail method. So I already actually have it set up here, but let's start with a vector plus b vector. So if you want to perform this addition, first you draw the a vector. Then what you do is you draw the b vector, starting with its tail at the head of a vector, and draw it out to here, just like I already had it drawn. The resultant vector, so a plus b, is actually starting from the tail of a to the head of b. So this would be a plus b. So that's great. That's how you add two vectors together. It should be very, very basic for you. But what about this? Does a plus b equal b plus a? Commutativity. Does these two summations equal each other? Or do these summations equal each other? So to do that, we're actually going to start by drawing b first. So I'm going to draw b down here. And then in the rules of addition, doing it graphically, we start drawing a from the head of b. So since it's the first term, second term starts from the head of b, goes up, and this is our a vector. And our resultant vector, the tail of b going to the head of a, is b plus a. So the question is, does a plus b vector equal b plus a vector? And I'm going to say yes. And here's why. I'm going to draw these down here again. So we have a, and I'm just going to draw them all in black for now. A, b, but from the same starting point, I'm going to start with b, and then a. And then a. So, we know the a plus b route will get us to this endpoint, and we know the b plus a route will get us to the same point. So each of these have the same resultant vector. So this is commutativity of addition in vectors. And we're going to write this in our little important sidebar here. So a plus b is equal to b plus a. So, congratulations. You're probably thinking I just wasted, a couple minutes learning something I've already done. Well, let's move on to another property of vector arithmetic and vector algebra, which is associativity. So you may be thinking, congratulations, I just wasted the last couple minutes learning something I've already done. Well, let's get into something a little bit more complex, which may not be as intuitive, just saying a plus b is equal to b plus a, and that is associativity of addition within vectors. And to do this, I have to introduce a third vector, c. So let me redraw our vectors here. So we have our a vector in black. We have our B vector, I'm going to draw in blue this time. So B for blue. And C for purple. So I'm going to draw C vector like this. So when I'm talking about associativity, normally when you hear that, you associate it with parentheses, and it has to do with the order of operations. So let's say that we have this first summation. A plus B plus C. How this works is by order of operations. We perform the summation within the parentheses first, followed by adding C to it. So let's actually do that. So from last time, or from the last example, we know that A plus B will end us up here. Let me actually write out what vector it is. And our resultant vector, which I'm just going to draw in black again, is A plus B. And I'm just going to wrap it in parentheses so it looks familiar. So now we can add C to this. And we're going to start C from the head, just like we've always been doing with addition. Put the tail of C on the head and draw it. This is C vector. Now we have this vector down here, starting from our initial point, going to the head of C. This is A plus B plus C. But hopefully you're thinking, I've kind of seen this before. You know the other side of this equation, which says A plus B plus C. And these are all vectors. Question is this statement true? So let's do it first. Let's draw it out. So once again, according to our rules of addition, or rules of operation, order of operations, we perform B plus C first. So, sorry for that. So we're going to perform B plus C. So I'm going to start B down here. So B. We're going to add C. And we get our resultant vector, which I'm going to keep in blue. This, and just say these hit the same point and these start at the same point. This is B vector plus C vector. Once again, we can wrap them in parentheses just to make it look a little bit more familiar. Now, let's add A. So starting from this tail point, or starting from the head, we're going to add A. And A kind of comes up a little bit sharp here, like that. This is A hat. Our final resultant vector of this whole thing starts from our initial point and goes to the head of A. This is A plus B. And if this form kind of confuses you, we already went over commutivity vector addition, so you can move these around, moving the parenthesis and the A around so it looks a little bit more familiar. And hopefully you can see that these two vectors are the same. If not, we can very easily, I'm going to erase this guy here, and I'm going to draw B here. Sorry about that. So this is B vector, starting from the same point. I'm going to put C vector down here. This is C. We have the resultant vector, B plus C. Then we add A. And look at that. All of these form the same resultant vector, showing you that vector multiplication is actually associative. Now let's actually leave arithmetic and go into something a little bit more algebraic. So what I mean is we're actually going to start multiplying some things together. But I want to be very, 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 very clear. We are only going to be, in this section, multiplying vectors by scalars. Multiplying a vector by a vector is actually two separate sections in the book. They follow a completely different set of rules, and it's not as simple as what you've been doing since middle school. So to show this, we're going to show scalability of a vector. So what I mean is, let's have our b vector back again. So here's our b vector. What if I were to say 2b? So kind of like saying, 2 times 3 is equal to 6. And by now, hopefully, you can just spit that off the top of your head. But how do you get to that number? Well, we know that 2 times 3 is equal to 6 because it's 2 3 times, or it's 3 2 times. I like doing the 3 2 times because it's less writing. Because we know it's 3 plus 3. Replace this with an x, so a variable. We know it's equal to 2x, and we know that this is equal to x plus x. Same thing with a vector. So if we say 2 times b, it's equal to b vector plus b vector. So if we have our b vector, and we add, the same way we were doing tail to head, another b vector, this resultant vector, starting from the initial point out to the end head, is actually 2b. That's scalability. What about 3b? What about 3.5b? So that's all scalability is. It's multiplying a vector by a scalar. But the question also arises, what happens if you have a scalar multiplying a sum of vectors? So that would be in the form of some vector. I'm going to stick with 2. It's very easy to work with. Times an a vector plus b vector. What happens, and how can we actually represent this another way? So here's our a vector that we've come to know and love. And here's our b vector. And we know the summation, a plus b, gives us this. But using the same definition of adding multiple things, or adding things multiple times, we know that 2 times this summation is just going to be this vector added to itself. Again, for 2. Pretty easy to see. But is there another way that we can write this? And the answer is yes. It's distributing. So we can actually distribute this 2 inside of these parentheses. And what's interesting is this allows you a nicer view of the vector, and when we start actually talking about components, this view is going to be the most popular. So how can we prove that this is true? Well, you can do it a couple ways. You can start by saying, I'm going to multiply a by 2. So we know that that's a. I am horrible at this drawing thing. There's going to be some interesting cutting. So we take a, add another a vector to it. This whole vector here is 2a. Then we can add 2 times b, which we know is just a b vector plus a b vector. And look, we end up at the same point, a same resultant vector. And one more interesting way that you can approach this, going back to our first definition, is it's the summation of a plus b 2 times. So before we just said, okay, we're going to take our summation and double it. But what if you actually perform the summation again? So we have a plus b, and we get a resultant vector. If we add another a, and unfortunately it didn't line up too well, and then we add another b, which is right here, we can see that we also get the same vector. So that's the distributive rule of scaling a summation of vectors. So you can actually move this scalar inside. But what about in a little bit more of a complex system? How about combining distribution with scalability, with commutivity and all that, and bringing it together into one final property? Which the book likes to point out because it is kind of a very popular topic that you're going to be seeing often in your problems. And that is when you have a sum of two scalars and multiplying it by a sum of two vectors. This looks like r plus s a hat plus b hat. R and s are just scalars. However, since we're dealing with algebra, we're not going to say that r and s are defined. We're just going to call them variables. We don't know their value. So we're going to keep them as that, and then we're going to say a and b are just two arbitrary vectors. So one of the ways that you can go about trying to figure out how can I actually shorten this or expand it is by saying, okay, we know these are two scalars. We know two scalars can add together. So we're going to make a substitution and say r plus s is equal to some other scalar v. And by having r plus s is equal to v, it kind of simplifies the problem a lot. Now you may be yelling, at your screen, why the hell don't you just FOIL this? We're getting to that. So v is just equal to r plus s. Now we know from our previous example, we can just distribute this inside the parentheses. So this is going to be equal to v times a hat plus v times b, not hat. Now let's resubstitute our r plus s back in. And we have r plus s plus r plus s b hat. So now we know that we can just move this in, treat it as one whole scalar, and multiply a and multiply b and sum it together. But what about individual scaling? And what I mean by that is, what about distributing this vector back into this parenthesis? Well, you know from your algebra that if we do that, it'll end up being r times a plus s times a. And at this point, if you look at it, we're not multiplying two vectors together, we're just multiplying scalars. So we can do that. So doing this, we have r a plus s a plus r plus r b plus sb. So we've shown basically that that's foiling. And if you wanted to group these together, you could do this with algebra. Once again, simplifying the problem. You can actually simplify this to combine all the r terms together. Sorry for slanting. And now you have every form possible of this distribution. And using all of these can be very helpful when we start getting into converting between different coordinate systems, because what ends up happening is that by using this distribution, you can actually start canceling out terms and start getting them equal to constants. So with this knowledge, you're able to move on, and I'm hoping this whole video was just a review, that you know this. But if you do not understand the algebra that just happened in this video, please be sure to do practice on your own. Contact the instructor. of the course or the lab tech, and we'll give you help. But you really need to understand these fundamental concepts of vector algebra.